We're going to go over section 13.1, the parabola part. We didn't cover that the other day. Parabolas are part of a bigger topic called conic sections, and in particular the parabola has lots of different uses. I kind of like this part to show you where you actually use the shape of a parabola. You'll see it in suspension bridges. You'll see it in certain types of telescopes called Newtonian telescopes. Radio telescopes have been using these things for over 50 years. These are amazingly sensitive. If you were to strike a match on the moon, they can spot the flare from Earth. Angry Birds has a parametric form of a parabola here. A Hubble Space Telescope uses a parabolic-shaped mirror, and this guy is named Andrew Feustel, who is an OCC graduate. So when we say you can get anywhere from here, yes, we mean it. All right. Here's a parabolic mirror on the top of a building, and they use that to collect sunlight and bring it down into the interior of a building with a fiber optic cable. So pretty cool. Searchlights and headlights use parabolic mirrors. Parabolic-shaped mics. Here's a solar collector at Delta College, which is up, I think, near Saginaw. This one's kind of cool. I want to do this. This is on my bucket list to take a ride on this plane called the Vomit Comet. And what it does is it streaks you up at a very, very steep angle, and then in a parabolic-shaped arc, it starts heading back down towards Earth. And while you're on that parabolic-shaped arc, you experience weightlessness, which is kind of cool. Does anyone see anything unusual about one of these pictures? Yeah, somebody put a cat there, which is too funny. All right, so let's work with them. Now, they're going to be a little bit different than what we've had in our previous sections. So let's start with problem number 44, which is x is 2y squared. And see what happens when we start trying to graph that. So there you go. X is 2y squared. So, okay. Let's do this. Let's plug in some values here, but you might notice that we've got x solved for, not y. So instead of plugging in values for x, how about if we plug in values for y? So we'll plug in values like this. So for instance, when y equals 2, what does x equal? So y equals 2, x equals 8. And then we can do likewise, plug in a value for y of negative 1 and get x is 2. Yeah, 0 squared times 2 is still 0. And then on the flip side of things, we're going to get a symmetric set of points. 2 times 1 squared, 2 times 2 squared. So just like our parabola in x squared, you still get a symmetric set of points, but there is going to be a major difference when we graph these. So let's try and figure out what the major difference is. I'll start by plotting points at 8 and negative 2, which is down here. 2 and negative 1, 0, 0. 2 and 1, and 8 and 2. Up a little bit too high there. So scratch that one. Okay, looks good. What's different about this parabola than the parabolas we've done before? Yeah, it's sideways. It opens to the right, not up and down. It opens to the right. So like that there. And I'm going to do this that way. So there you go. You got a parabola that opens to the right. What do you think makes it open to the right as opposed to opening up and down? How come this is different than what we usually have? Yeah, you got an x equals something instead of a y equals something. You got a y squared term as opposed to an x squared term. So that's going to mean these are going to look a little bit different. Let's play around with some of the graphs of these things and see what they're like. We'll start with problem number 46. I call it 46-ish, and there's a little bit of a typo here. So let's rewrite it here as x equals 3 times y minus 2 squared minus 3. So that's the problem that we're going to graph. And as typical with a lot of these things, what I like to start out with is, okay, well, what do you, where's the vertex? And to figure that out, ask yourself, well, what do you put in to make the squared term equal to 0? 2 for what? 2 for y. Good. So let's put in a 2 for y and see what happens. So x and y. If I put in a 2 for y, well, let's do that down here. X equals 3 times 2 minus 2 squared minus 3, which is 3 times 0 squared. 0 minus 3 is negative 3. So the easy thing to get twisted on is the order you put these in. We first figured out what the y value was, and then that gave us the x. So put in negative 3, 2, not the other way around. Don't put in 2, negative 3. That'd be a much different looking point. Now there's a couple other types of points that we generally find when we're graphing these things. One of the things we often go for is the x-intercepts and the y-intercepts. Although that's going to be changed a little bit. You're going to have an x-intercept and a couple y-intercepts. How do you find the intercepts of any graph? Not just this one, but any graph. All right, I should know better than to ask you questions after an exam. My bad. So, yeah, something about a 0, right? So if I set x equal to 0, then what do I get? Well, I get what kind of points? Y-intercepts. All right. Yeah, good job. All right, there we go. Y-intercepts. Intercepts. So let's do that. That's going to require a modest amount of thinking on our part. We're going to get 0 equals 3 times y minus 2 squared minus 3. Okay. So, not so bad. If I move the 3 to the other side, that'd be one way to solve this. Really, this is a quadratic equation. It's not a bad idea at this point in the semester to think a little bit about how we have different ways to solve quadratic equations. What can we do? We can use the square root property. What other things can solve a quadratic equation? Quadratic formula, and the best one that we've done since Math 1100, factoring. Good job. So let's go for the square root property. I'm going to move the 3 to the other side where it changes signs. Any suggestions from here? Yeah, let's divide out the 3. By the way, you can't distribute the 3 into the y minus 2 unless you squared it first. So that leaves me with 1 equals y minus 2 squared. Take the square root on both sides. Now, one thing that I hope you remember when you take the square root is to do what? All right, nice job. Wow, in unison too. You guys have been practicing. Good job. Plus or minus here. Plus or minus 1 equals y minus 2. Now keep in mind that that represents 2 solutions. There's 2 possibilities here. Either 1 equals y minus 2 or negative 1 equals y minus 2. So I'll add 2 to both sides. 3 equals y. Adding 2 to both sides. 1 equals y. You could check it. You don't have to, but you could. Oh, they should both work, yeah. Now, let's plug those 2 points in to our little t-table just to keep track of them. We got those by setting x equal to 0. And when x was 0, y was 1, or y was 3. Those were our 2 possibilities. There's still one other type of point that I want. We found our y-intercepts. What else do you think I need? X-intercept. And to get the x-intercept, what should we do? Set y equals 0. So let's take care of that part. Set y equals 0. So that's going to be 0 excuse me. So y equals 0, x is going to be 3 times 0 minus 2 squared minus 3. So that's 3 times negative 2 squared, or 3 times 4 minus 3. 12 minus 3 is 9. Okay, and we're going to kind of run a little tight on room on this one, so let me think real quick if I can kind of fix that a little bit. Let's adjust the scale on the x-axis a little bit. Let's make this 4 and 8, and that'd be negative 4. So basically along the x-axis, each tick mark is worth 1. And then let's plot some points. So that last point, by the way, has coordinates of 9 and 0. So let's put that up here in our little t-table. We put in a 0 for y, we get a 9 for x. In fact, I'll start by graphing that point. That'll be right here. We have a couple other points. We'll start with the vertex next. So it'll be negative 3 and 2, which is all the way up here. So negative 3 and 2. And then what? 0 and 1. And 0 and 3. Okay. So let's see if we can't graph this then. So there's that one. And let me do the other side. So something like that. Parabolas are nice and smooth at the vertex. They have a line of symmetry here. Sometimes I ask for this line. I'll ask for its equation. The line of symmetry is going to go directly through the vertex. Can anyone tell me the equation of this line? Thank you. Y equals 2. Now x equal 2 would be a vertical line, so if I do ask you for the equation, please give me an equation. Don't just give me a number. All right. How are we looking on problem 46-ish? Okay there? All right. Let's try problem number 40. Let's see. We'll try 58 next. Try problem 58. So we'll kind of go in order. So in this case, our equation is x equals negative 2 times y minus 1 squared plus 2. So we're going to do kind of the same thing here that we did with the other one. That is, start by graphing the x and y-intercepts, find the vertex, and we'll see what kind of points we got. Draw a nice smooth parabola to connect it all. So let me come over here. I think I'll have plenty of room without infringing on my graph. So about over here, let's draw ourselves a little t-table. Let's start by figuring out the vertex. To figure out the vertex, start with the squared term. What makes the squared term equal to 0? 1. Now let's put in a 1 for y. Now if that term is 0, that disappears, this disappears, yeah, and you're left with a 2. So 2 and 1 are the coordinates of your vertex. Let's find some other points. What else can we find? All right, x and y intercepts. We'll start with, set, not little Freudian slip there. Set x equals 0. That was embarrassing. Maybe I shouldn't post this one. All right. Set x equal to 0. We get 0 equals negative 2 times y minus 1 squared plus 2. So again, let's solve using the square root property. In this case, I'll move the 2 to the left-hand side. Divide both sides by -2. So I get 1 equals y minus 1 squared. And kind of like the last one, what we're going to do is use the square root property to finish this up here. Plus or minus the square root of 1 equals the square root of y minus 1 squared. So there's two possibilities. Either 1 equals y minus 1 or -1 equals y minus 1. 2 equals y or 0 equals y. Now that's kind of curious there at that last one, that 0 equals y. And maybe we'll see the reason for that as we go looking for the x-intercept. What do we have to do to find the x-intercept? Set y equals 0. So this is kind of curious. We already got a y equals 0 here. So let's see what happens. And in hindsight, this might have been predictable, unless anyone wants to predict it now. If we set y equals 0, we get x equals -2 times 0 minus 1 squared plus 2, which is -2 times 1. What do I get for x? 0. So that's kind of strange. Last time I got 4 points. This time I only got 3 points. Let me list those points for myself on our little handout. So when we set x equal to 0, we got two possibilities. Either y was 0 or y was 2. But if you set y equals 0, you get x is 0. Well, okay. What's happening here is that this is both an x-intercept and a y-intercept. So that point kind of has two purposes. It's the x-intercept and your y-intercept. Let's plot these. So our first one is at 2 and 1, which is right here. 0, 0 is here. 0, 2 is here. This one's going to be different yet again. What's going to be different about this one as opposed to some of our other ones? Yeah, this one opens to the left. Why do you think this one opens to the left? Yeah, because of the -2 out in front here. That's what makes it open to the left. So that's something that I wanted you to see. You picked up on it really good, so that's nice. But this one opens to the left. Again, you would have an axis of symmetry that runs through here. You'd have the equation of y equals 1. I'm drawing it with a dashed line because it's not really part of the graph. Let's move on down to problem number 48. So if you look at this one, it might not be so easy. You might say, well, wait, I don't know. What's the vertex? Can anyone read off the vertex there for this one? If you can, you probably wouldn't be in this class. All right. So there is a little bit of a hint here, and that's to complete the square. So let me rewrite this over here, and we'll work on completing the square. X equals y squared plus 6y plus 8. The right-hand side is not, y plus something squared or y minus something squared. So I'm going to make that happen. To help that out, I'm first going to move that 8 to the other side. And now I've got to complete the square here. So now I've got to figure out what I'm going to add to both sides to make the right-hand side a perfect square. Yeah, good job. So hopefully you remember this process. You're going to take half that middle number. Half of 6 is 3. 3 squared is 9. So I'm going to put a 9 here. But if I add 9 to right-hand side, I have to add 9 to the left-hand side. Okay, let's keep going. 9 minus 8 is 1, so I get 1 plus x equals something squared. What do I square to get that term on the right-hand side? Good. Y plus 3 squared. Moving the 1 back to the right-hand side, that's in a little bit better form. Generally speaking, when I test this on an exam, I'll kind of separate this. This will be one problem, and then I'll give you another problem to graph, because I don't want to make you go all the way through and work with this one, because if you make a mistake getting this, well, then you're not going to get the graph. So I generally make those separate problems, but be ready for that. Let's work on the graph now. Again, we'll do ourselves a little t-table here. And this is why we complete the square here, is so that we can kind of look at this and figure out what the vertex is. In this case, anyone for the vertex? Nice, and in order. So -3 for y, -1 for x. So perfect. There's a couple other things that I need here. I need the x-intercepts and I need the y-intercepts. But I'm going to be a little bit clever about the way I get these things. Keep in mind that there was 2 different forms of this equation that I have. There's the top one here that we started out with, and then there's this one here that we ended up with. Now this one's great for determining the vertex, but what if I wanted to find, say, the x-intercept? What do I have to do to find the x-intercept? Set y equals 0. Where is it easier to put y equals 0, here or here? The first one. Yeah, absolutely. Because if I set y equals 0, what do I get for x? 8. You can just see those terms disappear right away. So 0, 8. Nice. What else do I need? I need to figure out where x is 0, what values of y correspond to that. And again, you've got your choice here. So let me remind you that if y equals 0, excuse me, if x equals 0, y squared plus 6y plus 8. There's lots of different ways you can solve this quadratic equation. You got the quadratic formula, completing the square, square root property, and factoring. Well, if you're going to use the square root property, then I'd use this one. But this is pretty nice. And like I said, I like to do a little review here when you're getting close to the final exam. How does this factor? Good. Y plus 2 and y plus 4. So what's that mean my solutions are? Good. -2 and -4. Beautiful. Now, would you have gotten the same thing had you put x equals 0 here? Sure. Move the 1 to the other side, take plus and minus square roots, mess around a little bit. But certainly factoring is very friendly, and when you can, probably should. So when I said x equals 0, I get y is -2 and -4 respectively. That gives me plenty of points. I can now graph these. So let me do that. So we'll start here with the vertex at -1 and -3. Then there's the x-intercept, which is 8 and 0. And the y-intercepts at -2 and -4 respectively. Draw yourself a nice smooth parabola. I'm going to draw half of it, and then I want to point out something for us. So there's half. And it was handy that I had a point over here to aim for. But let me remind you that the parabola is symmetric. In fact, its line of symmetry in this case is what? Y equals -3. Nice. So let me finish drawing that a little bit more. So this is y equals -3. Now take a look at this. Above the axis of symmetry, if you go up by 1, you find a y-intercept. If you go down 1, you find a y-intercept. Over here, if you go up 3, you find a point. So similarly speaking, I should be able to go down 3 and find another point. So if you want to get kind of like this free point to help guide your graph and draw a decent graph, then hey, you don't have to do anything other than realize that this is a symmetric graph. So very nice. Any follow-up on this one? Maybe I went too fast over something, or are we looking good on this one? Good there? All right. Well, let's keep going. I think I want to use this video, my set comment notwithstanding, because my parabola here looks much better than my parabola for my other attempt this morning. So that's pretty good. All right. One thing that was really nice for us in a lot of these problems is having this thing set up. So let's practice putting things into that special form. And for that, let's look at a couple more problems, starting with number 40. We're going back to a regular parabola in x squared, but we can still put it in that form. Now on an exam, you probably see the instructions to the effect, put this into this form. Now a could be 1, in fact in this problem it will be. H doesn't necessarily have to be reflecting something positive or negative, it could be, whatever. But the nice thing about this form is you can take a look at what the vertex is at a glance. So let's take care of that. I'll move the 5 to the left-hand side. -5 plus y equals x squared plus 4x. Equals x squared plus 4x. What number do I have to add here to complete the square? Good, 4. Remember to take half of the middle number is 2, squared is 4. So 4 here and 4 there. On the left-hand side, I end up with -1 plus y equals something squared. What do I square to get that right-hand side, that x squared plus 4x plus 4? X plus 2. Finally, I'll move the 1 back to the right-hand side and get y equals x plus 2 squared plus 1. So from here, you can just look at this and tell what the vertex is. What's the vertex? Macy? Good, -2 and 1. So let's draw that. By the way, which way is this graph going to open, up or down, or left or right? Up. So over 2, up 1. In fact, if you wanted to be really accurate, can anyone tell me what the y-intercept is? Y-intercept would be at 5, right? Set x equal to 0, you get 5. So it has to open up. And the nice thing here is that by opening up like that, or at least knowing what the graph looks like, it tells you something that you don't have to look for. The x-intercepts. Are there going to be any x-intercepts for this one? No, it doesn't cross the x-axis anywhere. In fact, if you went looking for them, if you went looking for the x-intercepts by setting y equals 0, what you would find is that this graph crosses the x-axis only in your imagination. right? You get imaginary numbers if you go looking for the x-intercept. So there aren't any. Makes sense. There's one last one that I'd like to do with you, and that's problem number 50. A little bit of a twist to this completing the square stuff. Y equals negative 2x squared plus 4x plus 1. All right, I've interchanged x and y. It's all right. It'll still work for this purpose. Kind of like our previous problems completing the square, I want to get the 1 to the other side. But I can't start looking at taking half of 4 and squaring it just yet. There's something I have to do before I complete the square. Yeah, I have to factor out that negative 2. I can't complete the square on something that has a number in front of the x squared term other than 1. So I'll factor out that negative 2. When I do, that's going to change the sign on both of those terms. So I'll get x squared minus 2x. Now I'm going to complete the square on what's inside there. But you have to factor out that coefficient of x squared first. Otherwise, the process that we know for completing the square wouldn't work. So let's look inside the parentheses. Same kind of deal as before inside the parentheses. What number is going to complete the square in here? Don't look at the negative 2 out front just yet. Let's finish this up in a minute and a half. Let's go. All right, half of negative 2 is negative 1. Negative 1 squared is 1. Good job, Nicole. Except I can't just put a 1 on the right-hand side or on the left-hand side. What do I have to put on the left-hand side to keep things in balance? By putting that 1 there, I'm really subtracting what number from the right-hand side? What happens if you distribute this? It becomes a negative 2, right? So you have a negative 2 here where you didn't have it here. So the net effect, negative 2 times 1, is that by putting that 1 there, I'm really subtracting 2 from the right-hand side. So if I subtract 2 from the right-hand side, I have to subtract 2 from the left-hand side. Or, in this case, I added negative 2. Now, on the left-hand side, negative 2 and negative 1 add together gives me y minus 3. On the right-hand side, that term in the parentheses is a perfect square. What do you square to get that? What binomial? X minus 1. And finally, I'll bring that 3 to the other side and end up with y equals negative 2 times x minus 1 squared plus 3. Okay. Fast and furious, but we got it done. Anything on problem number 50 that needs a further explanation there? Looking good? Okay. See ya.